All right, there's more. This is the last section we'll be covering for your exam 2. Exam 2 will cover section 2.6 on rational functions, chapter 3, chapter 7, and chapter 8. 4 sections of chapter 7, 5 sections of chapter 3, and these 3 sections of chapter 8. So we don't have division when it comes to matrices, right? We have an operations that's similar to division, though, and we use it in that way. And it's the inverse. To solve an equation, to solve an equation like ax equals b, let's find a color here. To find an equation, solve an equation such as ax equals b, what we might do is multiply each side of the equation by a inverse, right? If this was a 3x equals 7, I might multiply by 1/3. 1/3 is the reciprocal of 3. When it comes to matrices, we're not looking at reciprocal, we're looking at specifically inverse. And see, 1/3 is a reciprocal, but it's the multiplicative inverse also. And the multiplicative inverse is the property that allows us to multiply 1/3 by 3. So here, in order to get the identity on the left, to get a coefficient of 1x, we'll multiply by the inverse of a. Notice I'm multiplying by the inverse of a on the left here. So I have to multiply by the inverse of a on the left of b as well. I have to keep the order the same. I can't just willy-nilly multiply on the left here and multiply on the right on the other side. I have to keep the relative position of these all the same. The number a inverse is called the multiplicative inverse of a because a inverse times a equals 1. Now, what is this inverse? How do we find it? Yeah, I remember what I was supposed to have available here, and I don't have it, but you'll get to watch me type it. Here's the definition of an inverse square matrix. Let A be an n by n matrix, has to be square. I sub n is the n by n identity matrix. If there exists an inverse matrix, right, the inverse to make A times A inverse in either order the identity, then A to the negative 1 is called the inverse and is read as the inverse. So basically, if we have an inverse, when we multiply A and its inverse, we get the identity. Well, let's take a look at that right here. Show that B is the inverse of A, where A and B are as given. Now, if B is A inverse, then, let's finish our words here. AB is the identity and BA is the identity. Let's see. If I multiply row 1, negative 1, and 2 by column 1, 1, 1, row 1, column 2, row 2, column 1, and row 2, column 2, when I do all of my adding up here, negative 1 and 2 makes 1, 2 minus 2 is 0, negative 1 and 1 is 0, that's 2 minus 1 is 1. I get the identity. If I do it in the other order, now I'm looking at rows of B, columns of A, so I have 1, negative 2, column 1, negative 1, negative 1. Notice the first column has negative 1, negative 1. First row, 1 minus 2, 1 minus 2. And we simplify this, we get the identity as well. So we could check, right? It's like when we had a composition of functions. We could take the composition of two functions, and if you get x out, when you take the composition in either order, then we know they are inverse functions. Same idea, if you can multiply in either order and you get the identity out, then these are inverse matrices. All right, but that doesn't tell you how to find an inverse matrix. So let's look at how to find them. If a matrix A has an inverse, A is called invertible, or later in math, you'll see non-singular. Otherwise, A is called singular. Singular because it doesn't, it's a single. It doesn't have a match. It doesn't have its own inverse. Or it doesn't have an inverse. A non-square matrix cannot have an inverse. It just can't happen. So we're going to let A be a square matrix of order n. We're going to write the n by 2n matrix. Consists of the given matrix on the right and then augmented with the identity matrix on, that's the left, Identity matrix on the right. Then we're going to row reduce A to I, so do Gauss-Jordan elimination on the entire matrix. And what happens is once we get the identity on the left, the resulting inverse matrix is on the right. If you can't do this, if you can't find this, if you can't make this identity, then A is not invertible, and you should always check to make sure it works out. Now, I'm going to do one of these. I'm kind of going to do two of these. I'm going to put the whole thing on the screen, I think. There we go. If I want to find the inverse of A, just a simple 2 by 2. That's 1, 4, negative 1, negative 3. I'm going to first augment it and put the identity matrix on the other side so that I have A and the identity. I need to make a 1 right here. That's all golden. I'm going to make a 0 below it. In order to make a 0 below, I'll add row 1 and row 2. And when I do, my new row 2 will be 0, 1, 1, 1. I have a 1 here. Now I need to make a 0 above it. All right, this one I have to make a 0 below. But we're trying to get an identity matrix, so we have to do full Gauss-Jordan. So I'm going to take negative 4 times row 2 and add it to row 1. And I'll get a new row 1. 1, 0, negative 3, negative 4. Row 2 is 0, 1, 1, 1. Notice we have the identity matrix over here. And so on this side, we have the inverse. All right, there is our inverse matrix. Negative 3, negative 4. Second row, 1, 1. If you were to multiply these two matrices together, you would indeed find that they multiply to give you the identity. And that's not too bad, right? I was able to cram it in here. But the inverse of a 3 by 3 is absolutely ridiculous. All right, let's start. We have a 1. Oh, first we have to augment. Yeah, we have a 1. Fantastic. We need to make all zeros below it. So I did that here in black. I made a new row 2. I made a new row 3. And then I had a 1. Now I need to make a 0 above it. And I need to make a 0 below it. So I could add row 2 and row 1. Get a new row 1. I can add negative 4 times row 2 and add it to row 3. And we go here. Now I have a 1. And I need to make zeros above it. And I just don't have room. We have to keep going. So I'm going to show you something else. Not that, sorry. I almost put these nuts. Whoops. There we go. Come on. So what we're going to do is learn how to use this matrix tool of Desmos. Desmos.com for all your math needs. So we're going to use tab. 1, negative 1, 0, 1, 0, negative 1. 6, negative 2, negative 3. And enter. That's our matrix. Now I'm going to take matrix A, and I want to find the inverse. And look, there it is. And that is so much easier than this. Now, for a 2 by 2, I still wouldn't even use this method, but it's possible. It's totally doable. For a 3 by 3, to do the inverse, if you want to keep going on this method that I started, see if you get here. I think we could see where we're starting to get there. Yeah, I got the negative 2, negative 4, 1. That's not going to change anymore, but as I make zeros here, these ones will change. So desmos.com/matrix, you define your matrix, and then there's all these different things that we could do with it. Yes, even an RREF that I didn't mention, but I will during review week. All right, so I didn't finish this one because I would never do this one by hand. I would use the matrix calculator. And that goes for every level. I would never do that by hand. I think I've done it twice. But that was as a student, never as an instructor. I don't torture my students like that. Okay. Let's go back to actually using the process. Find the inverse of C, the matrix 2, 6, second row, 1, 3. I need to get a 1 up here, so all I did is switch rows 1 and 2, but I took the entire row 1, the entire row 2, switched them. I have a 1, I need to make a 0, so I'll multiply negative 2 times row 1, add it to row 2, and I'll get 0, 0, 1, 2 as my new row 2. But notice I can't make a 1. If I can't make a 1, this inverse process doesn't exist, and so no inverse exists. This matrix is called singular. Singular. It does not have an inverse. It doesn't have a buddy. So I mentioned that I probably wouldn't use this method even on a 2x2. Why? Well, that's something easy right up here. If A is a 2x2 matrix, given by the matrix shown, we're going to call it just A, B, C, D, then A is invertible if and only if AD minus BC is not 0. Check this out right here. 2 times 3 is 6. AD, right? Cross multiply. Minus 6 times 1. So 6 minus 6 is 0. Not invertible. All right, so with this little test, we would have known we didn't even have to try. But the cool thing is that if AD minus BC is not 0, then we have a formula for our inverse. And it tells us you switch positions of A and D, switch the sign of B, switch the sign of C, and then divide by this thing called the determinant. The denominator AD minus BC is called the determinant of a 2x2 matrix. And so this really should say find the determinant of A. It's 1 times 2 minus negative 2 times negative 5. So 2 minus 10 is negative 8. So I found the determinant, but I went along with it, and I just decided to find the inverse as well. I switched the places of the diagonal. The main diagonal, always top right to bottom left. Top left to bottom right. My right and left are opposite today. Switch these two. 1, 2 is now 2, 1. Change the sign of the 2, change the sign of the 5. Change the sign of the 2, change the sign of the 5. And we'll have 1 over this negative 8 discriminant. So that's a negative 2/8, which I simplified. Negative 2/8, which I simplified. Negative 5/8, and a negative 1/8 for the inverse. This is a far easier process than that. I use this process almost exclusively, and I encourage you to do so too. Here's how we could use it. If A is an invertible matrix, the system of linear equations represented by AX equals B has a unique solution given by X equals A inverse times B, right? We talked about that earlier. So in this system of equations, negative 4x plus 2y equals 6 and 11x minus 7y equals 3, we have a coefficient matrix, negative 4, 2, 11, negative 7. We have a variable matrix, x and y, and we have a solution matrix, 6, 3. This is AX equals B. So what we want is, we want to solve x equals A inverse times B. Well, to find A inverse, I look at A, and I determine its discriminant. Negative 4 times negative 7 is 28. 11 times 2 is 22. 28 minus 22 is 6. All right, it's a 6. I switch the places of the negative 7, negative 4, change the sign of the 2, change the sign of the 11, and multiply through by 1/6. So I'll have a negative 7/6, negative 1/3, negative 11/6, and negative 4/6, which is negative 2/3. Now I can multiply A inverse times my B matrix. So what is it? It's row 1 times column 1 is in row 1, column 1. Row 2, column 1 is in row 2, column 1. Notice the 6's and the 3's work out just perfect for us to have negative 7 minus 1, negative 11 minus 2, and we have our answers negative 8, negative 13. I'm going to show you that on the calculator as well. Let's take a look at this problem. I'm going to clear all. Let's define our matrix A. Let's clear all. Let's make a new matrix. It's a 2 by 2. It's going to be this matrix -4. Oh yeah, let's make this easier. All right, so we have our matrix A. I want a new matrix, B. B has 2 rows, 1 column, and it is 6, 3. So now what I want is A inverse times B. Well, looky there. -8, -13. We did the operation right, and we can check our work using Desmos. All right, we would do the exact same thing. Take our coefficient matrix, 1, -1, 0, 1, 0, -1, 6, -2, -3. That's our A. I use Desmos to find my inverse matrix. This was the one that we did up above. It was our previous one. And then I multiplied it by B, 3, 2, 0, and I got my X values. The other way that you could solve this, instead of the A inverse times B, we could define a new matrix, the augmented matrix. 1, -1, 0, 3, augmented with B. All right, second equation, second row, third equation, third row. And then we could do this RREF A, and it's going to give me the answers -12, -15, -14. So RREF, reduced row echelon form. It'll do all that Gauss-Jordan stuff for you. Yeah, it will. I didn't tell you. But I told you before the exam. All right, so desmos.com/matrix for all of your systems of equations and matrix needs. Yes, it will add matrices as well. All right, that is it for today. I will see you on Monday. I see the doctor tomorrow. The doctor's going to tell me I could go to work because I have to go back to work. I miss you guys. Have a good weekend. See you Monday.